Welcome to today's paper reading. Today's paper is titled LLMRA, Multi-modal Large Language Model-based Restoration Assistant. This paper was published on AR14 by Xiaoyu and colleagues from Tsinghua University and the Chinese University of Hong Kong. The paper addresses the significant impact of multimodal large language models, MLLMs, on various tasks due to their extensive knowledge and powerful perception and generation capabilities. However, it highlights an open research problem of applying MLLMs to low-level vision tasks. To bridge this gap, the authors introduced the Multimodal Large Language Model-based Restoration Assistant, LLMRA. This framework leverages the capabilities of MLLMs to obtain degradation information for universal image restoration. By employing a pretrained multimodal large language model and a vision language model, text descriptions are generated and encoded as context embeddings with degradation information. These embeddings are integrated into the restoration network through the proposed Context Enhanced Module, CM, and Degradation Context-Based Transformer Network, DCFormer, contributing to more accurate and adjustable image restoration. The paper begins by introducing multimodal large language models, MLLMs, such as LLMRA, MiniGPT-4, and InstructLib, which have shown significant capabilities in high-level perception and vision language tasks. It then shifts focus to image restoration, a fundamental task aiming to recover high-quality images from degraded ones, involving various subtasks like denoising and derang. The current methods, however, are limited by being trained on datasets with single types of degradation. The paper also discusses the emerging interest in unified image restoration, where a single model handles diverse degradations, though existing techniques face limitations in real-world applications. Figure 1 illustrates the operation of the proposed LLMRA for universal image restoration. The system takes an input image and a text query requesting low-level attributes of the image, generating corresponding descriptions. When given the restore command, LLMRA automatically uses degradation descriptions from the MLLM to restore the image. Alternatively, with the refine command, LLMRA adjusts the image restoration process based on the dialogue content, allowing for iterative refinements to meet user satisfaction. In the field of image restoration, there has been limited exploration of unified methods for multi-degradation scenarios. Some studies have focused on specific weather conditions, but these often require specialized encoders or decoders, lacking scalability. AirNet, for example, uses contrastive learning to model degradation implicitly. In text-driven image generation, recent works have combined pre-trained generative models with clip-to-guide image creation. Latent diffusion models have also been proposed to train efficiently while maintaining quality. Multimodal large language models have advanced conversational AI by enabling models to understand and generate responses from both text and images, as seen in models like Flamingo, Blip2, and LLMRA. Figure 2 provides an overview of the proposed LLMRA framework for image restoration. Part A shows the LLMRA framework, which includes DN, CT, and DCFormer, used to refine and incorporate degradation information into the restoration network. Part B details the Context Enhanced Module, CM, which enhances text features to better represent image degradation. Part C illustrates the Context Transformer, CT, which processes these enhanced text features to generate degradation context C. This figure is crucial for understanding how the LLMRA framework integrates and refines degradation information to restore images effectively. The proposed method involves several key components. Firstly, the generation of text features is achieved using the IDEFX-9B instruct model, which processes both image and text inputs to generate coherent text features. This process is crucial for capturing the degradation information in the image. Secondly, the network architecture includes modules such as the Context Embedding Module, CM, and the Context Transformer, CT, which work together to enhance the degradation descriptions and generate the degradation context. Finally, the method employs distinct loss functions for training under different instructions. For the refine instruction, the refine loss is used, which focuses on reconstruction. For the restore instruction, the restore loss is employed, which includes both reconstruction and triplet losses to optimize the restoration process. Figure 3 illustrates the Degradation Modulation Module, DMM, within the DC-former architecture. The DMM is composed of an Image Cross-Attention Transformer, yellow box, a Concatenate Attention Feature Fusion, CFF, module, and a Basic Transformer block, blue box, from Restomer. The Basic Transformer block incorporates Multi-Conv Head Transposed Attention, MBTA, and Gated Conv Feed Forward Network, GDFN, for enhanced feature interactions. The CFF module processes feature maps to local and global branches to preserve intricate details and incorporate global context, respectively. This design allows the DC former to effectively restore images by considering specific degradation characteristics. Figure 4 presents visual comparisons of our method with state-of-the-art, SOTA, approaches across 3 image restoration tasks: image denoising, image derang, and low-light image enhancement. The first 2 rows show the results of image denoising on the Urban 100 dataset, where our method effectively removes noise without causing excessive blurring. The middle 2 rows demonstrate the effectiveness of our approach in the image derang task on the RAIN 100L dataset, successfully eliminating rain streaks and producing clear images. The last 2 rows illustrate the low-light image enhancement results on the LLV1 dataset, where our method enhances visibility and natural color without introducing artifacts or noise. The evaluation of the proposed LLMRA was conducted on 3 representative image restoration tasks: image denoising, image derang, and low-light image enhancement. A unified model was trained to handle all 3 degradation types. The architecture of the DC former includes a 4-level encoder-decoder with varying numbers of transformer blocks at each level. The model employs 4 DMMs and has a channel size of 48. It was trained with a batch size of 4 using the Atom Optimizer for 800,000 iterations. Table 1 provides a detailed comparison of denoising methods in both single-task and all-in-one settings across the BSD68 and Urban 100 datasets. The table highlights the performance of various methods, including DNCNN, IRCNN, FFDNet, AirNet, DAClip, and PromptIR, under different noise levels, sigma equals 15, 25, 50. Notably, the proposed LLMRA method achieves the highest PSNR/SSIM results, particularly showing a significant improvement of 0.39 dB over PromptIR for the highest noise level, sigma equals 50, on the Urban 100 dataset. The optimal and suboptimal results are clearly marked, aiding in the direct comparison of method effectiveness. Table 2 presents the derang results on the RAIN 100L dataset, comparing methods under both single-task and all-in-one settings. The table highlights the optimal and suboptimal results using bold and underlined text, respectively. Key metrics include the peak signal-to-noise ratio, PSNR, and structural similarity index, SSIM. The optimal PSNR achieved is 38.93, while the optimal SSIM is 0.984. The suboptimal PSNR is noted at 37.32. These results indicate the effectiveness of the methods in removing rain streaks from images, with the best-performing method significantly outperforming others in both PSNR and SSIM metrics. Table 3 presents the results of low-light image enhancement methods on the LLV1 dataset. The table is divided into 2 sections: methods under single-task setting and those under all-in-one setting. The performance metrics, PSNR and SSIM, are used to evaluate the quality of the enhanced images. The optimal and suboptimal results are highlighted using bold and underlined text, respectively, to facilitate comparison. This table provides a comprehensive view of how different methods perform in enhancing low-light images, considering both single-task and all-in-one settings. Table 5 presents an ablation study examining the impact of the CEM, Contextual Embedding Module, on image restoration performance across 3 datasets: BSD68, RAIN 100L, and LLV1. The results are quantified using PSNR, peak signal-to-noise ratio, and SSIM, structural similarity index, metrics. The table clearly highlights the best results in boldface, demonstrating the effectiveness of incorporating CEM in the restoration process. For instance, on the BSD68 dataset with a noise level of sigma equals 50, The inclusion of CEMs significantly improves the PSNR from 25.18 to 28.11 and the SSIM from 0.6913 to 0.7964. Similarly, for the RAIN 100L dataset, the PSNR improves from 26.54 to 38.64 and the SSIM from 0.8838 to 0.9831. On the LOV1 dataset, the PSNR and SSIM also show notable enhancements from 17.51 to 20.19 and from 0.6999 to 0.8243, respectively. These results underscore the critical role of CEM in achieving superior image restoration outcomes. Table 6 presents the results of an ablation study focusing on the method of modulating text features. The study evaluates the performance on 3 datasets: BSD68, RAIN 100L, and LOV1. The results indicate that the proposed method, which utilizes DMEMS, degradation context-based transformer network, outperforms the baseline without DMM in all datasets. Specifically, on BSD68, the PSNR/SSIM values are 28.13/0.7930 with DMM versus 28.02/0.7913 without DMM. On RAIN 100L, the values are 38.93/0.9842 with DMM and 37.71/0.9796 without DMM. On LOV1, the values are 23.30/0.8457 with DMM and 19.40/0.8013 without DMM. These results underscore the effectiveness of incorporating DMM for text feature modulation in image restoration tasks. The LLMRA framework introduced in this paper leverages multimodal large language models for universal image restoration. It uses a text-guided restoration network and a context-enhanced module to achieve more accurate and adjustable restoration. Experimental results show significant performance in image denoising, derang, and low-light enhancement. However, the framework's performance can vary with the MLLM's output, and it is currently limited to 3 tasks. Future work aims to expand the scope to include more restoration tasks. Figure 5 illustrates the impact of text input on image restoration tasks. The first row showcases image denoising from BSD68 with a noise level of sigma equals 50. When ground truth text descriptions are used, such as the image is well lit. No rain streaks detected. The image has Gaussian noise degradation and the noise level is high. Effective noise removal is achieved. In contrast, using ground false text descriptions, like the image is dark. The image is degraded by rain streaks. No noise detected results in persistent noise but enhanced lighting. This demonstrates the critical role of accurate text input in the restoration process, as supported by the quantitative results in Table 4. Table 4 presents the quantitative results of the impact of text input on image restoration across 3 datasets: BSD68, RAIN 100L, and LOV1. The table differentiates between with GT text, ground truth text descriptions, and with GF text, ground false text descriptions. For BSD68, the ground truth text input yields a PSNR/SSIM of 28.13/0.7930, while the ground false text input results in 14.46/0.4790. Similarly, on the RAIN 100L dataset, ground truth text input achieves 38.93/0.9842, compared to 20.11/0.8302 with ground false text. On LOV1, the ground truth text input shows 23.30/0.8457, whereas the ground false text input results in 7.59/0.1440. These results highlight the significant difference in restoration performance based on the accuracy of the text input. Thank you for watching.